Okay, so let us discuss rolling motion. Okay, so rolling motion is described as translation of center of mass plus rotation about center of mass. Okay, so translation of center of mass and rotation about center of mass is occurring simultaneously in rolling motion. Okay, so let me tell you two things. One, rolling can only be achieved or sustained on a rough surface. Okay, so without friction rolling can neither be achieved nor be sustained. Okay, this role of friction, what it plays in case of rolling motion, we will understand as we will discuss about this motion in this video. Okay, and the second thing is rolling are of two types. One is called the uniform rolling and another is called the accelerated rolling. Okay, so in this video we will talk about uniform rolling. Okay, about accelerated rolling or rolling in inclined plane, that type of problems have been already discussed in another video. Okay, so here see, suppose a particle is there, a rigid body is there, the translational velocity of center of mass is v0 initially. So think about the rotational velocity. Okay, that is the angular velocity about the center of mass is omega 0 initially. Now think about the bottommost point, the point which is in contact with the surface. As it is a rigid body, since the center of mass has a velocity v0, this point has also must obtain the velocity, translational velocity v0, and because of this omega 0, because of this angular velocity, this bottommost point will have a tangential linear velocity in the backward direction, which is omega 0 r. Okay, let this be r. Okay, the radius of the object which is going to roll on the surface. Okay, now see case 1. Okay, let v0 is greater than omega 0 r. Okay, so for this case, as v0 is greater than omega 0 r, the bottommost point will slip in the forward direction. It is a case of forward slip. Okay, fine. So as this point slips in the forward direction, the friction acts backward. Friction acts backward in this direction. Okay, now you see friction is acting against the translational motion. Okay, so there will be a translational retardation. Okay, and you see friction is creating a torque about the center of mass. The only external force is the friction, because normal reaction has been nullified by the weight of this body. So only external force is friction, which is causing the torque about the center of mass, for which it is rotating about center of mass. So now friction rotates it clockwise. Okay, so obviously this clockwise angular velocity omega 0 will increase because of friction. So there will be an angular acceleration. Okay, angular acceleration. Now you see here V0 was greater than omega 0 r. Now here V0, because of translational retardation, V0 is decreasing, and because of angular acceleration the omega 0 is increasing. So omega 0 r will also increase. So V0 was greater than omega 0 r, but now V0 is decreasing and omega 0 r is increasing. So ultimately at some moment V0 will decrease to V and omega 0 r will increase to omega r, and they both will be equal at some later instant, right? Clear? So when that will happen, when say at this moment the center of mass velocity becomes v after a time t, and the angular velocity about center of mass becomes omega. So for the bottommost point there will be a velocity v in the forward direction and a linear velocity omega r in the backward direction, and they will be equal. So when v equals omega r, when this thing happens, you see this bottommost point will no longer slip, neither in the forward direction nor in the backward direction. So it will obtain, the body will obtain a pure rolling motion. Okay, it will have an undisturbed rolling motion. No slipping is there at the point of contact, okay, with the surface. Okay, so it just rolls undisturbed. Okay, it's pure rolling. So the condition of pure rolling will be v equals omega r. Okay, so also we can write dv dt is r d omega dt. So we can say it is a equals r alpha. Okay, acceleration of center of mass is equals r into angular acceleration about center of mass. Okay, so this is the condition of pure rolling. Okay, so you see when v becomes equal to omega r, what happens? This bottommost point no longer slips. Okay, so there is no friction anymore. Okay, fine. So if there is no friction, then v will no longer decrease and omega will no longer increase. Okay, so v will remain the same, omega r will remain the same. Okay, so this equality relation will hold for the next span of time until it rolls. Okay, so v and omega no longer changes. Okay, fine. Okay, that's why it is called the uniform rolling. Okay, now you got the meaning of uniform rolling. V and omega will not change with time once the rolling is attained. Okay, fine. So v equals omega r, it's the pure rolling. Okay, so actually one question may surface your mind that, sir, if there is no friction once after the pure rolling is attained, so why does a rolling body eventually stops? Okay, it's a valid question. Okay, so the friction what I am talking about is actually the sliding friction. The sliding friction no longer acts, but there is a frictional force acts on a rolling body. Okay, and that friction is called the rolling friction. Okay, which has a very small value, so we are neglecting that friction here. We are not discussing about rolling friction here. So but rolling friction exists. So there is a friction, however small, acts on the rolling body. So because of that friction there is dissipation of energy, and because of that dissipation of energy a rolling body also eventually stops. Okay, it does not continue indefinitely, obviously we know it from our experience. Okay, so actually this case of pure rolling you have studied earlier in your childhood, you have studied it. See why? For this condition V equals omega r, what we can write? V is ds by dt and omega is d theta by dt. So we can write ds is r d theta. Okay, so if we integrate this thing for 0 to 2 pi and it is 0 to s, we get s equals 2 pi r. Okay, so see, we know that if this wheel of radius r, okay, makes a complete 360-degree rotation and goes there, okay, a complete 360-degree rotation and goes there, okay, fine, in the next position. Okay, that's why we have integrated this from 0 to 2 pi, complete 360-degree rotation. Okay, we know the displacement of the center of mass from our childhood, we know this thing. If the wheel rotates by 360 degree, it makes a complete, makes a full rotation, then the displacement of the center of mass is the circumference of the wheel, isn't it? We know it since our childhood. So see, s equals 2 pi r, here is the proof. So in our childhood we didn't know about rolling motion, but we actually have applied the condition of pure rolling. Okay, v equals omega r, and that's why we obtained this thing. Okay, so if there was slipping, we would have never obtained this thing, that for full rotation of a wheel, the center of mass, the center of the wheel will make a displacement equal to the circumference of the wheel. Okay, so now case 2 will be a lot easier now. Suppose v0 and it is omega 0. So for the bottommost point it will have a velocity v0, and in the backward direction it will have omega 0. Now if v0 is lesser than omega 0 r, so the bottommost point, this velocity is greater, this one is smaller, so the bottommost point will now have a backward slip. Okay, so for the backward slip the friction will act forward. And for that friction there will be a translational acceleration, because this force of friction, the only external force, because normal reaction is nullified by the weight, so only external force F is aiding to the motion of center of mass, so there will be translational acceleration. And now see, this friction will try to rotate this body in the backward direction, isn't it? This will try to rotate it in the backward direction, in the anti-clockwise direction. So actually it is rotating in the clockwise direction, friction wants to rotate it in the anti-clockwise direction, so it is opposing the rotation, friction, basically the torque produced by the friction about the center of mass is opposing the actual rotation of the wheel or the rolling body. Okay, so there will be angular retardation. So you see here v0 was lesser than omega 0 r, Now for translational acceleration v0 increasing and for angular retardation omega 0 decreasing, so omega 0 are decreasing. So after a while it attains a greater value v and omega 0 r decreases to omega r. Now these two things becomes equal, and when it becomes equal we obtain pure rolling of the body. Okay, clear? So after a while this is v and this is omega, so this is v equals omega r. Okay, so v equals omega r is pure rolling. Okay, so the first case was attaining pure rolling from a forward slip, and second case is obtaining or attaining pure rolling from a backward slip motion. Okay, clear? Okay, so how to approach a rolling numericals? Okay, rolling motion numericals. Okay, see, follow these steps for doing the numericals. First, identify the case of forward slip or backward slip. Okay, identify the direction of friction. Then write the equation of motion for translation of center of mass, which is F external is equals MACM. We know we have already derived this thing for an extended object in the chapter system of motion of system of particles. Okay, fine. Here is a rigid body is the extended object, the rolling body here. Okay, so the translation of center of mass and rotation about center of mass, which is external torque, is I alpha. Okay, fine. This one also you have learnt in this chapter. Okay, fine. So you have to write the equation of motion for the translation of center of mass and rotation about center of mass separately. Okay, but remember here this torque, this moment of inertia and the angular acceleration all are referred to the center of mass. All these quantities are taken about the center of mass. Okay, remember this thing very clearly. Okay, now the third step, write the kinematical equation for translation of center of mass and rotation about center of mass separately. Okay, we know for translation the equations are like this: v0 plus minus at s v0 t plus minus half at square, and v square is v0 square plus minus 2as, and the kinematical equations for rotation is omega 0 plus minus alpha t, theta is omega 0 t plus minus alpha t square, and omega square is omega 0 square plus minus 2 alpha theta. Okay, then put the value of I, that is the moment of inertia for the object. You see, the object which is rolling can be a solid sphere, can be as well a hollow sphere, can be a disc, or can be a ring. So you have to put the value of I accordingly. Okay, you have to memorize the values of moment of inertia of these rolling bodies. Okay, so put the exact value of I accordingly and do algebraic manipulation. Okay, so these are the 4 steps to do rolling motion numericals. Okay, so this approach will help you in doing the numericals. Okay, now let us discuss about rolling energy. Okay, the kinetic energy of a rolling body. See here, the kinetic energy will be the kinetic energy for translation of center of mass plus the rotational kinetic energy about center of mass. Okay, so it is the translational kinetic energy of center of mass and it is the rotational kinetic energy about center of mass. Because these two motions are occurring simultaneously in rolling, so the total kinetic energy will be given by, known as the rolling energy, is half m vcm square plus half I omega square. This is the rotational kinetic energy you have already studied in this chapter, right? Okay, fine. But remember, this I and this omega, these quantities are referred to the center of mass. Okay, these quantities are taken about the center of mass. Okay, fine. So it is the translational kinetic energy of center of mass, this is the rotational kinetic energy about the center of mass. All right. See this problem on a sphere of mass m, a force, external force is acting tangentially at the highest point of the sphere. Okay, clear? Fine. So the friction acts in this direction F. So here let me write, for the translation of center of mass, the net external force is F plus F. Okay, normal reaction is nullified by weight, so I am not writing that, I am not bothered about that here. So F plus F is ma. Okay, a is the acceleration of the center of mass, and you see here capital F is producing a torque in the clockwise direction and friction is producing a torque in the anti-clockwise direction. So these two torques actually oppose each other. Okay, so the net torque which is creating the rotation about center of mass will be net torque will be Fr minus small fr. Okay, that is F minus F into R. So now let us write the equation of motion for rotation about the center of mass, which is net torque is I alpha. Okay, so it is F minus F into R. Now this is a solid sphere, so it is 2 by 5 mr square alpha. This F minus Fr. So F minus F becomes 2 by 5 mr alpha. Okay, so we know for pure rolling A equals R alpha. So here it will become F minus F is 2 by 5 ma. So now I am getting two equations, F plus F is ma and F minus F is 2 by 5 ma. So let us solve these two equations. Okay, just add these two equations. What you will get? 2f will be 7 by 5 ma. So a will be 10f by 7m. Okay, this is the acceleration of center of mass of the sphere. They asked you this thing. Okay, fine. Okay, so it is a problem regarding the rolling energy. See, a carpet is there. Okay, so it is given a small push. Okay, now it is unrolling. Okay, it was wrapped up, now it is getting unwrapped. Okay, fine. So it says that length is L and the radius is R. So it says when during the unrolling, obviously the carpet will become narrower. Okay, so when the radius becomes R by 2, length will be the same, or you can understand, but when the radius becomes R by 2, okay, in this problem they asked you to find the velocity of the center of mass. Okay, so what we have to do, just conserve the mechanical energy. Okay, so conserve mechanical energy. But before that, suppose the mass of the carpet, when it was wrapped up, it was rolled completely, then it was m, and when it is unrolling and have a radius r by 2, then the mass is m by 2. This is m dashed, it will not be m by 2. This is what we have to calculate, m dashed. Okay, so if the density is rho, then mass is density into volume, right? So it is m is rho into the volume is pi r square L. But when it is m dashed, it will be, density is the same, length also same, but the radius changes, pi r by 2 square into L. So m dashed is rho pi r square L by 4. So it becomes m by 4. Okay, fine. Now the mechanical energy, initially call it EI and finally call it EF. Okay, so it is UI plus KI, it is UF plus KF. So initially, what is the potential energy? Suppose from the ground it was at a height of r, right, the radius, so it was mgr, the initial potential energy. The initial kinetic energy was 0, and then during the unrolling, when the radius is r by 2, the center of mass is at a height of r by 2. Okay, it is having a mass m dashed. So the final potential energy will be m dash g r by 2. Okay, fine. And the kinetic energy will be the rolling energy. Okay, so it will be half m dash v square plus half I omega square. Okay, so it will be mgr equals to m dash is m by 4 g r by 2 plus half m by 4 v square plus, now what is I? the moment of inertia of cylinder is half m r square. So it will be half m dashed, and it will become r by 2 square. Okay, fine, into omega square. Okay, again we know this for pure rolling v equals omega, right? Okay, for pure rolling we have v equals omega. So here it will be v equals, say, what we can write, v equals omega, and what is r? R by 2. Okay, so omega will be 2v by r, right? So omega square will be here 4v square by r square. Fine. So now let us write, this is mgr, this is mgr by 8, plus this is mv square by 8, plus 1 by 4 m by 4 r square by 4 into 4v square by r square. So r square will be cancelled and 4 will be cancelled. So this will be, if mgr by 8 comes in this, say mgr minus mgr by 8 is 7 mgr by 8, and here it will be mv square by 8 plus mv square by 16. So let us cancel m on both sides. So it is 7 gr by 8, it will be 16, 2 plus 1, 3v square. So it will be 2. So v square will be 14 gr by 3, and v will be root over 14 gr by 3. This is the velocity of the center of mass as they asked. Okay, clear? Fine. Now let us discuss another problem. It is known as the condition of no toppling. Okay, suppose a car is making a circular turn on a horizontal road. Okay, this is two wheels, this is the car. Fine. Now it is the center of mass of the car. Now what will be the maximum velocity of this car during the circular turn for which it will not topple? Okay, see, one thing, we have already discussed the condition of no skidding, isn't it? In the chapter UCM, Uniform Circular Motion, we have already discussed about condition of no skidding. Okay, it was v equals v lesser than equals root mu srg, isn't it? Okay, now it is not about skidding, it is about toppling. Okay, so what will be the maximum velocity for which it will not topple? Okay, beyond that velocity the car will topple. Okay, so see, let the friction acting on this car, on this wheel is F1, and on this wheel it is F2. Okay, the distance between the two wheels is 2a, suppose. Okay, fine. So it is the center of the circular turn, center of curvature. Okay, so F1 plus F2 is certainly the centripetal force, that is mv square by r. Fine. Now this is the normal reaction force N1 and this is N2, okay, on the two wheels. Okay, fine. See one thing, and this is mg clearly. So N1 plus N2 will obviously be mg. Okay, fine. So we can obviously write, you see, if we take these frictions to be limiting frictions, then we can obviously write mu s n1 plus mu s n2 is mv square by r. So obviously mu s n1 plus n2 is mv square by r. So it will be, oh wait, now n1 plus n2 is mg, so we'll get and see v square is mu s rg, so v equals root mu s rg. So this is the maximum velocity for which it will not topple, it will not skid, sorry, okay, which we already derived. Okay, so it's the same result. But what is the velocity for which it will not topple? See how to calculate this. We have to calculate the torque of these forces about the center of mass or center of gravity, whatever you want to call it. mg is passing through the center of mass, so it will not have any torque about the center of mass, but other forces will have. Okay, see, F1 will have an anti-clockwise torque about this point G. Okay, so is F2, anti-clockwise torque about the center of mass. N1 will have anti-clockwise torque about center of mass. Only N2 will have a clockwise torque about center of mass. Okay, so you see the anti-clockwise torques, these three torques, anti-clockwise torques, actually trying to topple this car. Okay, but the clockwise torque is trying to make it stable. Okay, staying on the ground. Okay, so because of the clockwise torque, the car stays on the ground. Okay, but because of the anti-clockwise torques, they tend the car to topple. Okay, so in order not to topple, we must have the clockwise torque is equal to the anti-clockwise torques. So suppose, let us write, see, suppose the center of mass is at a height of h from the ground. Okay, so the torque of the frictional forces will be because of the frictional forces will be F1 plus F2 forces into the perpendicular distance h about the center of mass. So this is anti-clockwise torque, plus another anti-clockwise torque will be N1 into A. Okay, obviously this length is A, the total distance between the wheels 2A. So center of mass, I am assuming that it is uniform, and center of mass lies in the middle, in between the two wheels. Okay, so it is A and it is A also. So from N1 the perpendicular distance is A, from N2 the perpendicular distance is A, so N1A. So these torques are anti-clockwise torques which are trying to topple the car, and the clockwise torque is N2A which is trying to stabilize the car. So what will happen? N2 minus N1 into A is F1 plus F2 into H. Now what is F1 plus F2? It is mv square by R. So N2 minus N1 into A, it is mv square H by R. Okay, so N2 minus N1 is mv square H by AR. Okay, fine. And we have already written N1 plus N2 is mg, so we will write N2 plus N1 is mg. Okay, so you see N2 solving, what we will get? These two equations, if we add them up, we get 2N2 is this plus mv square H by AR plus mg, and N2 will be half of this. And if we subtract them, then N2 will be gone, N1 will be half mv square H by A mg minus this, sorry, mg minus mv square H by AR. Okay, now see, N2 cannot be 0, it is always greater than 0. Okay, that means this will always stay on ground whatever be the situation, but N1 can be 0. Okay, if N1 becomes 0, you see, if N1 becomes 0, that means the normal reaction on this car on this wheel becoming 0. On this wheel it is not 0, never 0. But if this wheel, the normal reaction is 0, that means this wheel is losing contact with the ground. So this wheel is in air. So you can understand, when this will happen, the car will topple about this second wheel. Okay, about the left wheel. When the right wheel will be in the air, then the car will topple about the left wheel. Okay, well, the left wheel being centered, the car will topple. Okay, so N1 becomes 0. So that means when N1 becomes 0, put N1 equals 0, so half will go. Okay, 2 into 0 is 0, so this part is 0. Okay, so mg equals this, we get, implies mv square H by AR equals mg. Okay, so we will have v square equals ARG by H. Okay, so V equals root over ARG by H. Okay, so when the velocity will exceed this value, then the car will topple. In order to avoid toppling, the car must take the circular turn on the horizontal road having velocity below this value. Okay, so this is the condition of no toppling. So you see, for no toppling, the car can, without toppling, without the accident, the car can execute a circular turn if with a high velocity if H is lesser and A is greater. Okay, that means if the car executes, if the car carries out a circular turn on the horizontal road with a high velocity, its wheels has to be far apart and the center of gravity will be or should be as close to ground as possible. Okay, fine. Okay, so the in one word we can say that, so in one word we can say, if the car has to carry out a circular turn with a high velocity, its base has to be wide. Okay, wide base and heavy base. That means the center of gravity or center of mass, whatever you call it, is closer to ground. Okay, you will see this in the design of the racing car. Okay, in the racing car are very short in height. Okay, the racing car are short in height, they are stub. Okay, and the base is very wide, the distance between the wheels is large. Okay, only for this reason, because they have very high velocity, so while making circular turn they should not topple. That's why the racing cars are designed like this. Okay, also in order not to skid, the mu s, the tires are designed like that the mu s is very much, is enough to prevent skidding. Okay, with high velocity circular turn. All right.